everybody getting settled in? I think if we're getting settled, we'll go ahead and kick off. All right, so welcome to ARC334, everybody. This is building resilient applications on AWS with Capital One. My name is Andrew Baird. This is Mo Banahani from Capital One. And thank you to everybody here for coming out in person to the edge of the conference. We appreciate it. Everybody that's on simulcast, hello. There's two other venues that are watching this, and hi to everybody on YouTube in the future, including future Andrew, who's probably tempted to click like on his own video, so don't do that. Avoid the temptation. So here's how we're gonna cover the agenda today. I'm gonna cover the first half of the presentation. I'm gonna click this clicker 60 times in the next 30 minutes or so I'm gonna move quickly. If there's any questions you have specifically, we'll hang out afterwards if you want to dive deeper into any particular topic. But I'm going to cover a set of principles and patterns and guidance that we think is going to apply to everybody's architecture, hopefully, in the room. I'm not going to go into super deep detail on any one particular pattern. That probably would only apply to a very small slice of your applications, because doing things mission critical with resilience is going to be a very application-focused set of requirements and patterns. So I'm not gonna go super deep. There's other sessions that are dedicated to things like multi-region patterns and architectures that will give you all those things. So I'm gonna cover a bunch of topics I think will apply to everybody in the room, hopefully benefit everyone here. And then Mo is gonna go into some more specific examples for how Capital One's solving these topics and some architecture patterns that they use in particular to do some mission critical application operations inside of their portfolio. Thanks, Mo. Mo's going to come up on the stage in a little bit, so let's dig in. So a couple guiding principles. If you've been to reInvent before, you've seen many of our presentations in resilience, you're probably familiar with this quote from our CTO, Werner Vogels: everything fails all the time. I'm going to pair that with a second guiding principle quote from one of the founding members of VC2, and that's the failures that are going to happen all the time, you can't legislate against them happening. Focus on fast detection of those failures and response. So you want to combine those two principles, that everything is going to fail, and the mindset that anything within your architecture could fail and the application is going to be affected in whatever way it's going to be. And there's no real work you can do, no amount of diligence you can apply into the best practices you're going to follow to prevent those failures from happening. You just need to be prepared for them to occur and to apply the diligence in a way that's going to help you recover as fast as possible so that your customers are impacted as little as possible. And I'm going to make an analogy to the automobile. So there's a couple different ways that like resilience and failure detection and protection are implemented in a car. A lot of features, especially in modern cars, are dedicated towards helping drivers prevent failure, preventing accidents. But there's still other components that are related to handling the failures when they've occurred. So you can't just focus on one side of the story and put all of your time and energy into like the design architecture, making sure that everything is built to be as redundant and robust and like thoroughly taking advantage of all the best practices and the features we have available, things like Aurora D-SQL, which we just announced today, which probably people in this room might be excited about if you're doing mission critical resilience things. You can't just focus on those things. You need to also focus on what is your team going to do, how's your application going to behave when failures do occur, and what actions are you going to take. So we have to get smarter about the failures that are probably going to happen to the applications we build. So let's take an example, kind of the most simple example that a lot of people think about when talking about resilience on AWS, the multi-AZ architecture design. We've got a three-tier app here. We've got a primary and a secondary database. Say AZ1 goes away. A nice clean failure scenario, the conditions and the behavior of our application in that state. We're going to have a hard down inside that AZ. Hopefully, all of the managed features of things like Amazon RDS are going to kick in. We're going to fail over your database instance to the secondary instance, and then when things come back up, the event's over and traffic's able to recover to your primary instance. But everything's managed for you. We've got a hard down event, easy to detect, easy for managed features to kick in. Now, another scenario, which is possible as well, let's say that there's a particular issue with a connection between AZ1's application tier and the primary database. And service availability looks a little more like this, right? Maybe from the Amazon infrastructure point of view, everything looks healthy from our side. Maybe it's an application issue. Maybe it's a single host that's got faulty memory that's causing issues for your customer. Maybe there's a single network connection inside our infrastructure that's flapping. Maybe there's a single database query that's timing out on a particular instance because of the memory state or because of the user access patterns or something. And you end up having a scenario like this that's that's much harder to just take advantage of all of the design things you've built in using the features that we provide for you out of the box. But if this is a mission-critical application for you, this could be a really painful day. So how do you take that into account? So we like to think about all those different failure scenarios landing in this kind of 2x2 grid of the perspective of the system state for being healthy or unhealthy versus what your customers' perspectives are. And the top right quadrant is really the one where a lot of the focus of today's conversation is going to live, gray failure. So where the features and the observability and the systems that you've built that are about resilience and recovery believe everything is healthy, but your customers are experiencing pain right now. So that's what a gray failure is. They're hard to detect, they're hard to prevent, they're hard to mitigate, and the way that you account for them, and the way that you plan for them more deeply is by building better observability, because this grid is all about the perspective of health, right? So the better your observability is, the more granularity you build into your observability to detect when your customers are experiencing pain, the more you can push those failure scenarios into these other grids where it's you're in a position, or you've done enough work ahead of time to put yourself in a position to move the failure scenarios into different quadrants that are easier to take action based on. So the way that we're going to think about that, or the way that we're going to be more robust in building mission-critical resilience, is we're going to focus on these three things. We're going to focus on fault isolation, observability, and recovery, and we're going to connect them all together at the end. So for fault isolation, this is usually where people immediately jump to when they're designing their AWS architecture. They think about their physical design, how the different services we offer come in these different buckets of physical availability. Are they zonal in nature? Do they have redundancy at the zone level built into them, and they operate at the regional level? Are they global services that we offer where, regardless of where your application's built, they're accessing our services that operate at edge locations like in Route 53 and CloudFront? And this is an important aspect of the design, and you have to get it right, but this is where our customers typically, in my experience, spend almost all of their resilience-focused time, is making sure that they've chosen the right physical design fault boundaries in their architectures to ensure they have the right amount of redundance, they're meeting the RTO and RPO goals that they have, and it's important, but it's typically not enough. So there's also logical boundaries that you're going to build in, and I think we're not going to dive too deeply in here, but this is another example of how logical boundaries are part of the resilience story too. So we've gone from monoliths to microservices, some type of service-oriented architecture that's going to give us the ability to have other isolation boundaries between different components so that they can fail independently, that they can scale independently, they can be deployed to independently. All of those things are going to change the dynamics for how we can attack the topic of resilience and define kind of the ownership of it across different service boundaries. But there's other ways that you can kind of logically define boundaries inside of AWS. Multiple AWS accounts is another example of a good logical failure boundary. There's certain operations that might happen inside your team that live at the AWS account level. There are things like service quotas and limits that exist at the AWS account level. So the more you can think about that being a logical boundary between components of your applications, the smaller the blast radiuses, or the other failure scenarios you might be eliminating from within your architecture. And then a pattern that Mo's going to dive into a little more specifically that I'm going to highlight, and you've probably heard us talk about it before if you've been to many of our resilience topics. This is an architecture pattern that is pretty ubiquitously followed inside our newer services inside of AWS, and our engineering teams at AWS are strong advocates for the cellular architecture. So where rather than just thinking about the fault domains that you physically have laid out across availability zones, and the service-oriented architecture providing boundaries, but taking that stack and partitioning it into cells where you've divided either your customer base or however you think about the workloads of your particular application, and what a partition might mean for it, and dedicating those to an independent stack of the whole service ecosystem within that cell that's deployed to independently, is operated independently, and has its own dedicated infrastructure and dedicated services. So each one of these is providing kind of the full suite of capabilities that like vertical stack of business capabilities is provided by those services. And if anything were to go wrong, logically or physically, to your architecture, you have another boundary here where you're hopefully isolating what the impact is going to be across all your customers by having repartitioned them into another set of boundaries. And the net new layer that Mo's going to talk a little more about as well is this idea of a cell router. Now that you've deployed your architecture across these partitions, how do you know which partition, when a request comes in, that customer is assigned to? So there's this new component called the cell router that's going to observe the request coming in and route it to the appropriate stack. But I'm going to go pretty quickly through here because Mo's going to spend a little more time on it too. So all of that represents kind of your new service ecosystem. So again, the idea is to take the design elements that you've maybe been thinking at the forefront about for your AWS architecture designs for a long time, which is the physical design of our infrastructure and how it relates to AZs and regions and what capabilities are provided by our services, and realize that there's still yet another way in which your own ownership of kind of the architecture design logically can like further take advantage of introducing even more partitioning and smaller impact radiuses through concepts like cell-based architectures. So you want to be conscious of the mechanisms and patterns available. The boundaries that you define are going to dictate the amount of isolation that can exist when failures occur. The smaller the blast radius can be when failures do happen, because they will happen. And in reality, the failures that you're going to experience are not going to be those clean, neat, kind of coarse-grained, black and white failure scenarios where everything has come down and it's easy to detect and easy to recover from. So that's fault isolation. We're going to talk about observability, which I think is maybe the most important and also oftentimes the most neglected aspect of resilience and achieving good resilience among our customers. So if you come away from this conversation and take one thing with you that you're really going to like prioritize and light a fire under for your team with to achieve better resilience, I really think observability is probably an area that almost every customer I've talked to can improve in some way. So we've already harped on this a lot. Failure is not binary, but the way that you make the failures appear to be more binary at a more fine-grained level is by having good observability. So here's an example where at the top, typical metric that a customer might see, they have a service called My Service. They're observing what the latency looks like for all their customers. Everything looks a little noisy, but everything looks to be within ranges of normal. But you have a lot of customers complaining that they're having a bad day. Your executives are being told that there's a lot of pain out there, but your metrics just don't show it. So if we were to look a little closer and divide our metrics up across our AZs and look at that metric at an AZ level granularity, we'll see that there's one particular AZ. Maybe it's not receiving as much traffic as the other AZs are, so it's easily hidden inside the aggregated metric, but there's a clear inflection point that's happening where maybe some pain is being caused. So being able to have the right level of granularity in your observability at the forefront of your dashboards and your alarming is kind of key to being able to decide and to understand when those pain points are happening for customers. So here's another example. Maybe on the flip side, so we have an event where our query latency has really ballooned up in the middle of the day. Maybe it happened overnight. We had an alarm go off. We had an engineer that was investigating what happened. We have no reports of anything occurring for our customers. Everything seemed to be happy and smooth, but they were tempted to perform a rollback. They weren't sure what was going on, and then the situation kind of just resolved itself and went away, and nobody really knows what happened. Maybe we paged them in, and it's caused a lot of sentiment issues and pain for the team. But what if that scenario was defined by just that single metric kind of aggregating what the latency was for our database for all the queries that get sent to it? And maybe there's pretty different types of queries that we're sending to that database. Maybe one of them is retrieving items, but another one is submitting new orders if we're an e-commerce website. And if we were to have more fine-grained metrics that are tracking latency down at the query level, and dedicating dashboards to each query type individually, we might see that during that event, both of these metrics looked pretty normal. And maybe the query large metric that we have at the top there was a large bulk number of orders or a particular heavy user that was initiating a high number that's unusual for the longer query type that has more latency in the story. So even though everything looks normal when you split it up, it looked like a pretty painful event when you had your metrics aggregated. So again, the theme is really understanding what the dimensions are of your metrics and the appropriate granularity that your metrics should be reported at, so that the visibility you have into the architecture is as fine-grained as possible to really be able to track the level of granularity that behaviors exist inside your application, the way that you've designed it, the way you've deployed it, the way that it runs. This is an example of the put metric data API inside of CloudWatch. There's this attribute called dimensions where you can add a number of different attributes that uniquely identify that particular metric. So that particular metric is going to have these things associated with it. And we provide these dimensions out of the box for the metrics we publish about our services at CloudWatch. So when you go to like an EC2 instance, it's going to have a lot of dimensions associated with it, like the AZ that it's running in. But you want to use this concept of dimensions to adhere to the same file isolation boundaries and behavioral boundaries that exist inside of your design and your application. And once you've done that, you're going to have a robust amount of metrics and dimensions available for you to have a lot more granularity in your alarming and your investigations operationally. And so where do you apply those dimensions? This is another area where I think a lot of customers struggle. A lot of times our customers are really just measuring availability of the applications at the front. They've got requests maybe from a third-party monitoring tool that are hitting the front door of their API. They're determining if the service is available via that API, and things look great. But realistically, things can go wrong at every one of these links. And if things go wrong at every one of these links, it's going to define maybe a different type of failure scenario that your application is going to experience. And if all you're really monitoring is the front, maybe it's going to flag when an issue exists, but you're already setting yourself up for the initial investigation into any operational event being really dependent on understanding, kind of manually tracking through your service ecosystem where a failure might be experienced. And if you're relying on the humans to kind of dive into where the failures are occurring inside of your stack, you certainly haven't built any recovery automation or resilience at those individual levels where there's no observability and monitoring and alarming able to be taking place right now. So if you're really doing something mission critical, which is what this session is about, the expectation is that every single dependency you have and link between those dependencies within your stack is going to be independently monitored. You're going to understand the independent availability and the behavior and health of it. And in that aggregate picture, you're able to create, this is a pattern that we use pretty ubiquitously also at AWS and Amazon called composite alarms. Rather than expecting your engineers to have dozens or hundreds of individual high severity alarms that they've configured that could page them at any moment to come investigate what's happened, you take all of those individual metrics that represent the composite health of your application and all those dependencies, and you create a single alarm that is the composite view of overall application health, and that's where the alarm really kicks in and brings the human into the story to come and investigate. And they can tell in that composite alarm which is the underlying metric that's triggered the alarm to fire. So if you're doing all of those things well, there's almost this full cycle that you can implement, right? There's the instrumentation you've built, the amount of dimensions you've included in your observability, the depth of the metrics, the business-oriented metrics you're reporting from within your application and the dimensions associated with it, the amount of logs, metrics, and traces you're capturing that lead into alarms and dashboards and hopefully automated recovery, things we're going to talk about in a bit. And usually those things lead to questions, and the questions happen during investigation time. And if it's a mission-critical application, you probably have executives on the phone who are asking lots of questions about where's the impact, how long until we're recovered, what's this mean for our revenue, all those types of things. But if you really want to improve your operations without having to do it under fire, you want to be able to have those questions be asked on a more proactive and regular cadence. So this is a huge part of Amazon's culture, and if you're using AWS for running mission-critical things, and you're going to take away any of the things that we're sharing with you, this is another hugely important one we think is a big differentiator for how we've made operational excellence core to the culture inside of AWS. We have this mechanism called the weekly AWS Ops and Metrics Review. It's on the far right there. A weekly meeting that happens at AWS, and in reality, every one of those people on that slide probably represents like 100 or a couple hundred people inside of the organization that come and attend this meeting sometimes. So it's far and away one of the most expensive meetings that we operate as an organization, but one of the most critical to our culture as well, because it sets up this very proactive, mechanistic conversation that happens down within the individual teams where as part of their preparation to come into this weekly ops and metrics review, where questions can be asked about what the health of your service stack was the week prior, your team has had to do a lot of pre-work to investigate what has been our services health for the last week. Are there any anomalies that we see? Do we experience any operational events that we're going to get asked questions about? And by going through this process every single week and having every team prepare for it every single week, even if they haven't experienced any issues, they're either going to potentially uncover opportunities for improvement that are identified without having someone have been paged before. But also, if there are lessons learned by other teams who did experience events and want to, share how the recovery took place or what the incident was that they, their application or customers, succumbed to, they're going to learn about those things within this broader meeting where a lot of lessons are shared and stuff. So, creating the robust amount of observability needed to come into this meeting effectively and to be able to answer questions really completes that fly loop so that operations have a chance to continually improve, and not just in the context of like recovering from painful events that have happened where failures have occurred that that weren't handled very well. To kind of summarize the observability portion, the idea that the amount of investigation and recovery kind of robustness you can achieve is literally bound by how good your observability is. If you don't have observability that's down to the level of granularity that shows you where specifically your customers are experiencing pain or your application's exhibiting bad health, the more coarse-grained your recovery operations have to be, and the riskier they feel, and the more expensive they potentially are to implement. So the more granularity you get your observability down to, the more aggressive you can be about the types of actions you're going to take to recover and prevent failure from happening. So these are the ways, like the crumple zones of your application. The more granularity you add into your observability, the smaller those little crumple zones can be, and the more aggressive you can be about implementing them and taking action for them too. Where all of that granularity is achieved or should be achieved is going to be aligned to the default boundaries that you've implemented physically and logically, and having a good organizational mechanism that prescribes proactively everybody has to care about these things is the way that you get the flywheel spinning. So if you have a team or a department in your organization that really cares about operational excellence, I say champion that team to go and try and get some top-down sponsorship from a CTO or a CIO to implement that type of mechanism. We have a lot of published material online about how our metrics and operations meeting occurs, if you're interested in that. Okay, so let's talk about recovery now. So checkpoint, we've learned about how to isolate our designs, adding existing granularity into like where the blast radiuses of failure are going to occur. Just talked about observability. I don't need to rehash what we talked about there. But the reality is, so what? What have we done so far? We've done a really good job at taking advantage of the amount of like design redundancy available in the isolation we have, and we're able to tell where failures are happening. But in reality, like we're still going to experience those failures, and we might be really well versed and capable of understanding how to investigate them. But our customers are still going to experience pain unless we've implemented ways to recover from them. So this is like my favorite quote related to the space from mission critical resilience expert Mike Tyson, and this is what we see all the time with customers, and it's so frustrating to see that they've spent so much time and there's a lot of capability that they've implemented, tons of attention they've given the topic of resilience, and then a bad day happens and they feel handcuffed from taking any action, because as good as your planning is, if you're not comfortable taking the actions that you've set forward, that you've designed into your strategy, you're gonna feel paralyzed from acting. And we get a lot of questions during when we have a bad day or when customers have a bad day of like, do I have to push the big red button? When will you be back up so that I don't have to? And it's that type of hesitation that's a sign that you haven't quite focused on the right amount of things to prepare yourself for when the day goes bad and your application gets punched in the face and your customers are not having a good day. So let's talk about recovering. So first and foremost, the whole idea of the different isolation boundaries we've created has this concept of redundancy. So I'm not going to spend time like explaining how at multi-AZ databases you provide redundancy, but I'm going to talk a little bit about this concept of static stability, which is a little more advanced but equally important, especially if you're talking about mission-critical resilience. So static stability means that even in the face of failures, you're not dependent on your application taking any new actions in order to maintain operational health. That the ongoing operations of the application will continue in spite of failure occurring somewhere within the architecture. So your dependencies are not sharing the destiny of application health. So an example of this is auto-scaling groups. And this is where customers often have bad days that could have been avoided as well. Auto-scaling does a great job of providing new instances when failures are detected, but in reality, it's deploying net new EC2 instances in the event that these things are detected. And invoking that create instances API is an example of a new application behavior that's not really a part of the existing runtime for your application. It's a dependency that you're not exercising. It's part of normal operations. So there's a chance that if we're having a bad day in the EC2 service, that the launch instances API is also having a bad day, and we're not going to be able to satisfy the need to create new instances. So rather than having this dependence on autoscaling be your recovery mechanism, which calls the launch instances API, we don't want you to do this. Take an example from the Lambda service, which is all about already having the capacity that they believe they need provisioned in a warm pool of EC2 instances, and the mechanism for provisioning a new customer environment does not depend on launching a new instance in real time. Every time a new customer creates a Lambda function or we need to provision a new environment for them, we're not just invoking that launch instance API in real time to create it for them. We have a warm pool of those instances already, and the warm pool is running and dedicated to part of the Lambda service, and the Lambda service has its own control plane that is allocating capacity to customers as it's provisioned. But there's not any dependence that they've taken further on the EC2 service to take that capacity. They've pre-provisioned what they think is the appropriate amount of headroom for them to continue operating. So that's static stability. Next, we'll talk about retrying. Retrying is table stakes, but a lot of times our customers implement retrying in a way that makes their bad days worse. So when you have it implemented where every time a failure occurs, it could be transient in nature, it could have been a quick network blip, a connection being disconnected. You should retry things, but if you've implemented retries with not a lot of smarts to them, you're going to have a situation like this. We call them retry storms, where if every one of our service dependencies has a failure and makes a request twice to retry it, and our downstream service 3 is having a bad day and has gone down for a brief period of time, all of a sudden those amounts of retries, they start exponentially increasing, and all of a sudden the component that's having a bad day, all of the components in front of it are pounding it even further with the number of retries they're trying to implement. And we have this exponential retry storm that is pounding the component that's already struggling to, maybe it's having a memory load or capacity issue, and these things cause bad days to spiral and get worse. So you want to be smart about your retrying. And if you want to look at the AWS SDK, there's examples of how we implement this. But exponential backoff is an important strategy where for every one of those retries that happens, there should be an amount of backoff that occurs. So you're not just retrying as fast as you can as soon as it occurs, but there's an amount of backoff that happens between every one of those attempts. And the introduction of jitter is also not shown here, but important as well, so that every component isn't trying at exactly the same timestamp as well, that they've got a little bit of time jitter in there so that they're sending the requests at slightly different times. Client-side rate limiting is another example. So as you build services and provide your customers clients, instead of expecting them and their software to implement their own retry logic, just take ownership of that inside the client SDKs or libraries you provide your clients, and implement things like client-side rate limiting so that you protect your own service like we do. Like I said, if you look at our SDKs, you'll see things like this implemented inside of the SDK. Okay, again, I'm going to move quickly here so we can get to Capital One. All of this stuff will be on YouTube if you need to see any particular slides. Now, route around, I think, is maybe the most crucial component that we want people to think about in terms of recovery, because it's often the fastest way to get back to being healthy. Rather than recovering components that are failing, just avoiding sending traffic to things that are experiencing issues is a much simpler set of actions to take. And it almost always depends on health checks. So there's two types of health checks that we're going to focus on. The first is shallow. So shallow health checks are, an example, you might have like a health endpoint that is just telling you whether your service is up and running. It just checks that the service and application are available. There's nothing really being thoroughly checked in terms of the runtime behavior of the application. And then there's deep health checks where you are going to check your dependencies. You're going to run a more thorough set of of actions within the application, and you'll have a much fuller picture of what the overall health of the application is. And so an example of what behavior might be in each of those two scenarios, if we have ELB and we've got health checks that are happening at the shallow level, and there's a failure inside our application, we're not going to be really aware of that. We're still going to send traffic because the health checks are shallow and whatever failure is happening inside your dependency stack is not visible. The ELB is not going to route around that particular application component that's experiencing some problem. Maybe it's got a bad memory module or a leak occurred in some edge case that happened just on that instance. So with deep health checks, we have the idea where failures happen inside the instance, and we're able to detect that, and we're routing around that failing instance right now. And that's really straightforward when the failures occurred at the instance level. But what if we have a dependency failure? Say the dependency is having a bad day, and now all of our instances are showing that they're unhealthy. And the behavior that you're going to observe there is that now our ELB thinks every single instance is having a bad day, and autoscaling is going to try and incrementally replace every single one of those instances, when really it's our dependency that's having an issue. But now we've got this compounded failure situation where we're fighting against the intended behavior of autoscaling and the actions that it wants to take. So we're going to call this fleet aside, where autoscaling is kind of perpetually committing fleet aside against your stack. So this is the result. It's going to keep replacing those instances in 10 batch chunks. So if we take a mixed approach here, and we have deep health checks inside the ALB that are looking for deep application level health, but autoscaling is about the application behavior only, we're going to be able to detect that the great failures occurred and route around traffic when that's happened. But when a particular instance failures occurred, we're not going to detect that on the autoscaling group anymore. Because the autoscaling group is just looking at EC2 instance health. So we're able to route around correctly and not have that fleet aside happen, but we're not able to rely on autoscaling to replace our instance when there's application level issues that don't show up in the shallow health checks anymore. So the trade-offs there, which I'm going to get through quickly here, the deep health checks are going to, if you integrate deep health checks with autoscaling groups, you're really risking having that fleet aside set of actions take place. So if you implement deep health checks, don't associate those with autoscaling group rules, autoscaling group health checks. It does allow you to route on great failures, and it requires you to implement a more holistic mechanism for detecting when there's actual local instance health that autoscaling can depend on to scale your stack. For shallow health checks, it's easy to integrate those with autoscaling groups, but it requires you to build an additional mechanism to handle gray failures. So all those dependency issues where gray failures can happen. If you're going to implement shallow health checks, it means you need to take a more kind of separate from the ELB's built-in health check routing capabilities, implement your own thing for detecting when gray failures are occurring and taking instances out of service through automation that you've built. Okay, so neither of these is right or wrong, but there's different pros and cons, and the way that you apply them in your stack is really going to dictate if they're being used in the right way. And once you've done all that and you've gotten familiar with health checks, if you like the idea of routing around things and detecting when failures have occurred and how to avoid portions of your architecture that are being impacted, application recovery controller is the way to do that. So you have the ability to use ARC at the regional level, where we have the concept of a big red button, but in the case of this service, it's part of its data plane, it's not part of its control plane, so this still counts to us as an example of static stability, where that ability to push the big red button and the health checking that's happening across all of your stacks is part of that service's normal operations, rather than having to depend on a control plane API to shift traffic. And you can also have this occur at the zonal level as well, at the load balancer level too. I'm going to go through this. And the last bit we're going to focus on is returning to known good for your operation. So we have production deployments. This is an example from the white paper we have on the AWS Builders Library for what a production deployment sequence looks like for us. And the thing I want to call out here is that the sequence you see is aligned to all of the fault boundaries that we've defined, different AZs, different cells, different regions. And the way that we go through a deployment and let it bake and understand what the health of that component is during the bake time is all aligned to the way we've built our fault boundaries. So you want your deployment and resilience approach to be congruent to each other. You want to have your boundaries for recovery to align to the segments of the deployment pipeline actions you've taken. And the same types of actions you're taking during deployment, to safely ensure that changes are being made to application components aren't going to be changing in the middle of receiving requests. That sounds just like routing around components of an application. So you want the same code, the same execution steps to be symmetrical to each other. You want your resilience recovery actions to feel just like deployments. Summarizing the recovery, the things we've covered, static stability is an important component to make sure you're not taking these runtime dependencies that are net new in the middle of a failure scenario. Think about your retry logic and the best practices associated with it. Routing around is the number one recommended way to recover fast during failing scenarios, and make your recovery actions feel like deployments and vice versa. So how do you put that all together? It's going to look like this neat little virtuous cycle where you want to have all the physical boundaries that are physical and logical fault boundaries inform the dimensions that relate to your observability strategy, and for the boundaries that are defined by both your observability and your fault boundaries to equate to the way that you think about deployment. And the more robust and the more fine-grained you can get the story on this slide, the more prepared you are and the more granularity you're going to have to handle the failures that Werner is saying are going to happen all the time, and the more quickly you're going to be able to recover from the failures that you detect. So you build those things, you get as granular as possible, and then you test it. And if you want to test it, we have a service for that too called Fault Injection Simulator, which is going to let you have those different services at the bottom. They're different compute services and databases, networking, storage, and inject failures into your stack and see how your observability is going to catch things and the recovery actions you've built in are going to behave. And if you've done all these things well and you execute those actions of recovery as part of your normal deployments already, hopefully the next time your app gets punched in the face, you're going to be feeling much more comfortable to just execute the normal recovery route around actions that you always do as part of your deployment already anyway. Okay, I'm going to call Mo up, who's going to go another layer deeper and give you a lot more specifics on the Capital One side of the story.
Thank you. So, my name is Mo Banihani. I'm a distinguished engineer at Capital One. And I'm thrilled to be here today at AWS reInvent to share the Capital One journey in building resilient applications in the cloud. When I look back to my college days, I look back to my 18-year-old self in a new country, thousands of miles away from my family. And I was excited about all my new prospects, the new relationships I was about to build in this new environment. And little did I know that one of the first relationships that I built, other than people, was my relationship with my bank. It was a relationship built on trust and a relationship built on transparency. And this relationship helped me open new opportunities and new doors and exciting new adventures. And don't worry, it was not my last relationship. I'm happy to report back I'm married with 2 wonderful children. So things improved since then. But it's true. It was a relationship built on trust. A trust that I think all of us experience with our banks. We trust that our money is safe and secure, and we trust that we could get that money anytime we need it. And that's why at Capital One, we're very passionate about building applications in the cloud, but we're very passionate about the customer experience and how our customers experience those applications. It's not just about building great technology. It's about the experience our customers have with our applications and that trust that they instill in us for every system that we design. So today, I'll walk you through some of those examples and walk you through how we implement resilience in our applications. In the financial services sector, application resilience is weaved into everything that we do when it comes to application design. We implement it in our applications, we monitor it in our applications, and the way we operate them. Banks are also expected to provide a solid foundation for secure data transfers, great customer experiences, even under heavy workloads. At Capital One, our systems help provide the transparency and trust that are critical for our banking industry. That's why when we invest in our application resilience, we invest to make sure that not only we're mitigating risk, but we're also building and harnessing the relationships that we have with our clients. That's why when we design applications, we design them to deliver consistently, respond accurately, and react quickly when inevitable failures happen. So, our resilience approach constitutes in three different areas. Our first approach is our cross-region failover. We distribute our workloads across large regions or distances to ensure that when failure occurs in one region, we're able to support the other one. The second one is AZ distribution, and we distribute our workloads across multiple AZs to increase its availability. Lastly, we've introduced cell-based architecture into our resiliency model, and we're able to basically provide higher and more critical platforms, a higher level and higher degree of resiliency, which we'll discuss further more. But now to make all of these approaches work, we have to weave in a solid foundation for continuous monitoring and observability to ensure that we are alerting on issues when they happen, and we are notifying our team so they can react quickly when issues arise. So today we'll be talking about two platforms at Capital One that leverage cell architecture. The first one is our authorization platform, and the second one will be our core banking platform. In the first scenario, on the authorization side, we have a very high requirement for a tight execution for 250 milliseconds. We have an end-to-end execution chain that we need to execute within that 250 milliseconds. We also have to complete smaller transactions within that workflow or fall back to a degraded mode of operation. And on the core banking side, we have multiple applications across customers and partners that are all transacting against this core platform, which all of them have varying demands and scalability requirements that we have to support and cater towards. So let's start with our authorization platform. So you might be wondering, what is an authorization platform? Well, an authorization platform is a critical platform at a bank because it basically verifies and validates all the transactions incoming from our customers and millions of transactions on a daily basis. All of these critical events must be conducted in under 250 milliseconds to ensure that the customer experience is optimal. Imagine yourself as a customer, you swipe your credit card, you're making maybe a grocery run or checking into a hotel, and you sit there and you wait, and you wait, and you wait. Imagine if the transaction fails. What would you feel? What would our customers feel? And that's why when we designed the authorization platform, we designed it with speed in mind. So let's take a look at that architecture. So for the authorization platform, we've selected a zonal independence cell architecture. We are able to execute a full transaction within one AZ, or one cell in this instance. Again, the requirement here is for low latency, tight execution of those transactions. The data must remain consistent during the entirety of that transaction, even though it's being handled by independent services during that workflow. And we implemented a traffic router so we could distribute that traffic across replica cells using a Capital One developed algorithm. Once the transaction enters the cell, the entirety of that transaction is completed within that cell. Now, you might be thinking that's not a typical cell architecture, but it's a cell architecture that worked very well for us to achieve that low latency that we needed. And on the plus side, we're also able to save costs around data transfers between the AZs and regions. So let's look at the key attributes of this design. We have One, AZ affinity as a key attribute, and low latency as a key driver for us here. So we wanted to auto-scale within a cell. We canary into that cell before we fully operationalize it. And we, as I mentioned, fall back to a degraded mode. So we are avoiding retries at the cell level. On the low latency side, we had to implement a data sharding strategy to ensure that we're distributing traffic equally across our cells. And we wanted to maintain strong data consistency at an AZ level, but also eventual data consistency across our regions. So let's walk through some of the attributes of this design and some of the benefits that we've gained out of it. First one is the deep health check. So we've implemented deep health checks to accurately understand the health of our cells, all the way down to a transaction level. So by sending frequent traffic into that cell and alerting on all the failures or issues that might impact in that cell, we're able to understand the health of that cell and shift traffic when issues arise. As mentioned, this is a critical platform. So we can't afford to wait for customers to notice that these failures are occurring. So we must build a model to predict and understand what's going on in that cell. And before we breach our SLAs, we're able to transfer that traffic away from that impacted cell. We've also leveraged AWS CloudWatch and other observability tooling to help us funnel all of these alerts from our cells into our resilience engine so we could have a good snapshot of how our cells are performing and how our transactions are performing at each cell. So you might be wondering, what is this resilience engine? Well, the resilience engine is basically our active monitoring tool that monitors the health of all our cells all the way down to a transaction level. What's great about this is we're actually able to gather all of these alerts from CloudWatch and other observability tools, even from our own application and the transactions occurring on them. We're funneling this data into Amazon DynamoDB, and we're actually assigning a rating for every transaction. So not only we understand the health of the cell, but we also understand the health of each transaction occurring in that cell. Now, once we start noticing that there's a shift or a slip in our SLAs, or we're about to breach an SLA, the cell router, or the resilience engine, will issue a decision to shift traffic from one cell to another. And at the same time, we'll notify downstream teams that there's an issue that came up, so they could react quickly and address that need. Not only that, the actual resilience engine is able to also do other things, such as capacity management calculations, to see if we have enough cells, if we have enough capacity in that environment, and potentially create downstream actions to deploy further cells. Now, once a cell comes back into health, it will canary traffic into that cell to ensure that it is ready, and then begin to shift traffic back in. Now, another thing that we consider in this model is failover to another AZ. So as I mentioned, the resilience engine plays a critical role in measuring what is happening at the cell level all the way down to a transaction level. Now, once it detects something, as I mentioned, it will begin to shift that traffic away from that cell, and all of this is automated. So not only that we understand the health of the cell and the transaction, the resilience engine is also able to kind of predict when things go awry and begin to shift traffic preemptively before the customers notice it. All right, the last one is an interesting one that I wanted to share. So fall back to degraded mode. So in this instance, as I mentioned, we have a tight execution of 250 milliseconds. During that time, we're executing multiple workflows. And in those workflows, what we've done is we've created a method for us to actually issue multiple smaller decisions during the process before the full decision is completed. So the first decision will come through, and it will be a preliminary decision. It gets passed on to the next workflow. Then the second workflow will issue an updated decision, and so on until the full execution completes. Again, under 250 milliseconds. Now, the good thing about this architecture is, in case we breach that SLA, we'll always have an answer to send back to our customers, because again, we wanted to achieve that optimal experience for the customer. and that is only achieved if we do this in under 250 milliseconds. And this is a great example where business architecture and application architecture come together to design a high-performing system. So let's walk through the core banking platform. So you might be wondering, what is a core banking platform? A core banking platform is basically, when you think of dealing with a bank, is every transaction, every relationship that you have with a bank goes through a core banking platform. You might be thinking of a retail bank customer who's making deposit or issuing withdrawals, or you might be thinking of a credit card customer who has one or multiple credit cards with different preferences or varying payment methods. There's endless possibilities when you're working with the bank and endless transaction types that the core banking system must handle. Not only that, the core banking system must be resilient and accurate, because as a bank, you're expected to have good record keeping and excellent resilience. So you could only imagine how large this platform is and how complex this platform is. So what are we doing with this platform? In this instance, we've selected a different cell architecture approach. Here we are picking a regional cell-based approach. And in this model, we've actually focused on, rather like the authorization platform, which speed was the critical driver for us, here, tenant segmentation is the critical piece. In a large platform like this, with varying transactions occurring from different channels, each of these tenants have varying requirements and needs, from scalability to resiliency to the speed of how you respond to those transactions. Each of them, we have to cater for those customers and those tenants. So in this model, we're able to actually split our tenants across cells where we're providing them with better resilience and isolation. Not only that, we're actually able to cater to their specific needs. So if one tenant is expecting a high level of transactions, we could actually carve out that tenant into a different cell and handle them and scale them differently than the entire platform. And we could isolate from noisy neighbors that could potentially impact other tenants. So let's walk through the key attributes on this one. Here, again, our drivers were tenant isolation and dynamic tenancy support. On the tenant isolation side, we wanted to eliminate or at least control the blast radius that we had. We wanted to use a tenant router so we could split our tenants across cells and distribute its traffic there. We leveraged AWS IAM to also secure the data and create some data isolation when we're doing shared tenants. And lastly, eventual data consistency across regions was critical. On the tenancy support side, again, we wanted to support multiple tenant models. So we wanted to go with a both silo and pooled approach. Also, we wanted to minimize that noisy neighbor. When we know that we have specific customers that have higher transaction rates, we wanted to make sure that we are designing for them. And lastly, we wanted to have the ability to migrate our tenants across those models. Now, let's walk through some of the critical benefits of this design. On the core banking side, the biggest one for us was fault isolation. Now, with fault isolation, this gave us the flexibility to control our operation of such a large platform. It comes in handy in two places. We are able to isolate deployment failure, so it gives our teams more operational flexibility to experiment with software, experiment with their releases, and that they have the confidence to know that when they are experimenting, when they're releasing rapid software, they're able to know with comfort that this is contained to a specific customer or to a specific set of customers and will not have ripple effects across tenants. The other side is isolating emergent system failures, which at a cell level, because we're operating across regions, across multiple AZs, when we have failures at that level, we're able to also switch traffic to multiple AZs so we could make sure that that issue or that deployment failure, failure within the AZ is contained, again, to that one customer in that one boundary. Another key benefit is operating cells independently. And this one is an interesting one. When we think about failover for applications or large platforms, we think of it as a one-thing entity, meaning that we failed in this region, we take the entire application, move it to the second region, or not move it physically, but shifting the traffic to another region. And we handle that with that approach. Now, that requires a lot of operational capacity and requires a lot of diligence to achieve that goal. Imagine at a platform that size. So that complexity, and what we've done in that complexity is we were able to actually independently operate these cells separately than other cells. So, for example, in one cell, if we had a regional failure or we had an issue within that cell, we could actually operate that cell independently from others and move the traffic from one region to another without impacting the entire platform. And when you think about it, the benefit there is not only that we are containing that blast radius to one region, we're also making sure that we're not creating a chaos within our teams that are trying to rapidly address this issue, and we might be creating more noise for them if we're failing multiple cells or a large platform. Now, the last one is preventing retry storms. On this front, we are leveraging two AWS capabilities. One, we're leveraging AWS capabilities to help us fail over within our cells, so AWS Route 53 and Elastic Load Balancers, and those give us native features and capabilities to help us fail our application. Now, we've coupled that with exponential backoff and retries. And I know Andy mentioned length, but we are starting to leverage that to ensure that we are not creating retry storms within our application. And that if that happens, it's also contained within that cell, so we're not creating ripple effects across a large platform. So that cell architecture, along with that feature, helps us contain our blast radius in one place. So let's wrap it up. Again, your resilience journey is not a one-size-fits-all. You have to invest in understanding your application and your application requirement, and also your business drivers, to help you select the best resilience model for your application. Deep health checks are your friend. By leveraging deep health checks, you're able to understand how your application and workflows work at a detailed level and tailor your reaction time and your responses based on how that workflow works. Another one is continuous improvement is a continuous journey. It never ends. It's your job to look at your application, dig deeper into your architecture, and understand how your application works. When you do that, you're able to actually design at a component level failure modes to kind of combine into your overall resiliency posture. And lastly, which I think is something that a lot of us sometimes miss, is understand your business workflow before you begin design. As I mentioned earlier, we've designed for the authorization platform a multi-hop invocation path for us and multiple decisioning during that process. That's business design coming together with application design to design a more resilient and more higher throughput platform. And with that, I would like to say thank you for your time today. And I really appreciate the time you spent with us. And thanks again, Andy.
Yeah, thanks everybody. Please remember to fill out your surveys about the events, especially if you enjoyed the session. Thank you. Appreciate it again, everybody that came all the way to the edge of the conference for this. Thanks.